Okay, I think we can start. So Ashoke can proceed with his fourth lecture, please.
Okay, thank you. Can you see my screen?
Yes, yes, it is visible.
Okay, thank you. Okay, so last time I gave a general procedure for computing string amplitudes. Okay. So today what we are going to do is to apply it to a specific example. Okay, and the specific example that I'll be picking is the simplest that one can think of. So the 4-point amplitude. Of states V1 to V4. Okay, right now let me keep them arbitrary. Later on, we'll restrict to on-shell states. Okay. So the relevant moduli space here is M04, okay, which is 2-dimensional. Okay, so let me remind you that general formula 6G minus 6 plus 2N. So here G is 0 and N is 4. So that gives you two-dimensional moduli space. So the first task is to pick a section. Task is to pick a section of P04. And in general, any choice will do. Okay? Any choice of the transition function that we introduced. Okay, I'll again remind you what these were. Transition functions Fs parameterized by 2 parameters. By 2 parameters will do. I should say almost any choice. Okay, maybe almost. Because if you are unlucky, then you may parameterize by a parameters which can be removed by change of coordinates. Okay, but generically this will not happen. Okay, so let me then remind you what our procedure was. So we have 4-point function on a sphere. Okay, so this is our sphere. And you have 4 punctures. So first you have to divide it into regions using circles. So let me draw those regions. So let me first mark them 1, 2, 3, 4. So we draw some circles around these. So these are disks. And one more. Okay, so that each piece is a sphere with 3 holes. So this I'll call S1. This I'll call S2. And these circles, let me put orientation. I'll denote this by C1, C2, C3, C4, and C5. Okay. So the coordinates here, as usual, will be chosen as W1, W2, etc. So let me just write one of them. So this is W1, W2, W3, W4. And on the sphere, I'll choose these to be Z1 and these to be Z2. So now the relations, we have to introduce a transition function. So on C1, we have Z1 equal to F1 of W1. On C2, we have Z1 equal to F2 of W2. On C3, we take Z2 because C3 divides, this is Z2 and W3. So this is F3 of W3. On C4, we have Z2 equal to F4 of W4. And on C5, okay, this is where I'm going to introduce the two parameters. So on C5, I'll take Z1 to be minus Q by Z2. Here, Q is a complex parameter. Which is equivalent to two real parameters. Okay, this will eventually play the role of the parameter that labels the section. Okay, and note that I have taken the F1, F2, F3, and F4 have been taken to be Q independent. But this is just a matter of choice. Okay. In fact, I'll illustrate this by this example, but I'll leave it as an exercise to check that if whatever you do, right, even if you include some Q dependence on these functions, okay, eventually the final result for on-shell amplitudes remain the same. So our first task will be to construct the B's. Okay, so let me remind you the BQ, okay, by definition will be sum over S equal to 1 to 5 integral del Q of Fs B of Z1, sorry, let me call it B of sigma S. So sigma S, if you remember, is the coordinate to the left. Okay, and Fs is relating sigma S to tau S, which is the coordinate on the right. And then there is a holomorphic piece, the anti-holomorphic piece. Here, you see that only thing that depends on Q is Fs, okay, is F5. Okay, everything else has been chosen to be Q independent. So this, in this case, is integral del F5. So let me write this as del Q of minus Q over Z2 BZ1 DZ1. Okay. This one is 0 because Fs bar is F5 bar is minus Q bar over Z2 bar, but of course del Q of Q bar is 0. Q and Q bar can be taken to be independent. So only this remains. Okay. So this is just minus 1 over Z2, which is Z1 over Q. Okay. So this I can write as 1 over Q integral Z1 BZ1 DZ1. So this is along C5. And similarly, we can construct BQ bar, which will be 1 over Q bar times integral Z1 bar B bar Z1 bar DZ1 bar. This I'm going to write in the next slide. So B of Q bar. Okay. The only thing that depends on Q bar is F5 bar. So this will be integral C5. So with this, we can now write down the expression for the amplitude. So this is integral minus 2 pi I inverse. Okay, minus 2 pi I inverse. This, let me remind you, this came from a factor in that omega, the differential form, which had a minus 2 pi I to the power minus 3g minus 3 plus n. Okay, here G is 0 and N is 4. So that's minus 2 pi I inverse. Then there is GS. Okay, again, GS to the power appropriate power. 3G minus 3 plus N. So that's comes here. Then integral dq, which dq bar. And then inside, we have a q inverse times integral C5 B of Z1, Z1, dZ1. Then q bar inverse integral C5 B bar of Z1 bar, Z1 bar, dZ1 bar. And then we are using, let me explain this. Let me write this F1 dot V1 0, F2 dot V2 0. I'll explain what F tilde are. F tilde 3 dot V3 0, F tilde 4 dot V4 0. Okay, so what I have done here is the following. Okay. So once you have put this coordinate system, we can use this relation that I have chosen, Z1, Z2, Z1 equal to minus Q over Z2, okay, to think of Z1 as the coordinate system on the entire sphere. Okay, it's not necessary, it's just a choice. We could have taken Z2 or any SL2C transformation of Z1 or Z2. Okay, but I have chosen Z1 to be the coordinate system on the entire sphere. Okay. So then the local relationship between the local coordinate W1 and Z1 is just W1 equal to F1 of Z1. Okay, that's here. Similarly, W2 and Z2 is Z2 equal to F2 of W2. Sorry, here Z1 is F1 of W1. But here, what I need to do is to write things in terms of Z1. So Z1 is minus Q over Z2, so it's minus Q over F3. So that's what I'm calling F3 tilde in this. So F3 tilde is minus Q over F3. F3 tilde Z, let me write this. F3 tilde of W3 is minus Q over F3 of W3. And similarly, F4 tilde of W4 is minus Q over F4 of W4. I hope this is clear. Okay. So this gives the full amplitude. Okay. Now we are going to restrict to on-shell states. Okay. So now consider on-shell state. That means BRST invariant states. And as we discussed, that for BRST invariant states, we can choose a representative. And the representatives we will be choosing is Vi equal to CC bar Wi, okay, where Wi is dimension 1, 1, matter primary, matter sector primary. So matter basically means it's made of x's and the derivatives, and into the ik dot x. Okay, so this is, so then F1 dot V1, because V1 becomes a dimension 0 primary. So this just becomes a V1 of F1 0. So with this, we can now write the amplitude as minus 2 pi I inverse times GS times integral dq, which dq bar. I have taken out q inverse and q bar inverse, okay, which came from those integrals, contour integrals. Then inside this, you have integral C5 Z1 BZ1 dZ1 integral C5 Z1 bar. Then I have CC bar W1 of Y1. I'll explain what Y1 is. CC bar W2 of y2 cc bar w3 of minus q over y3 and cc bar w4 of minus q over y4. Okay, so what is y1? So y1 is nothing but f1 of 0. y2 is f2 of 0. y3 is f3 of 0. And y4 is f4 of 0. Because this is a matter sector primary, okay, no factor comes in the under the conformal transformation. All that happens is in the argument, we get v1 of f1 0, and f1 of 0 is what I'm calling y1, f2 of 0 is y2. Here you have v3 of f3 tilde of 0, but f3 tilde of 0 is minus q over f3 of 0. That's minus q over y3, and so on. So I hope this is clear. And the contour C5 encloses y3 and y4 in clockwise direction. Actually, in this case, it doesn't matter if it's clockwise or anti-clockwise because there are two of these integrals. Okay. But let's see why it encloses y3 and y4. We could also, of course, take it to be enclosing y1 and y2 on a sphere. So if we just look at this diagram, okay, you see that C5, this C5 has y1 and 2 on one side and 3 and 4 on the other side. Okay, so on this you can think of as enclosing 3 and 4, or 1 and 2. Okay, on this side, I'll take it to be enclosing 3 and 4, but it's a completely equivalent. Okay, so now I'm going to simplify even further. Again, let me just say that all these are choices. It's not the final answer is independent of these choices. Okay. We'll simplify further by taking y3 equal to infinity. By taking y3 equal to infinity and y4 equal to minus 1. Okay. Again, I'll leave it as an exercise to check that the final result doesn't depend on these choices. Okay, so exercise, final result doesn't depend on these choices. Okay, but let's make these choices anyway. So with this, then this argument becomes 0, and this becomes cc bar w4 of q. So A is minus 2 pi I inverse gs integral dq wedge dq bar q inverse q bar inverse. Then integral of C5 So geometrically, the picture is that we have this 3 and 4. Okay, and the contour is enclosing this, the two contours. Okay, and 1 and 2 are somewhere outside. Okay. So now I can deform this C5 contour because the integrand here is purely holomorphic, here it's purely anti-holomorphic. So two of these contours are there, because one for here, one from there. So let's take any one of them. Okay, so let's take this one. Okay. So I can deform this and try to pick up residues from 3 and 4. Okay, and the residues are in general non-zero because B, so B bar, for example, has a pole at C bar, okay, a single pole. Similarly, B bar has a pole at C bar. Similarly, this B has a pole at C and also a pole at C. But you can see that the residue from here, okay, will vanish because of this Z1 bar. Okay, B bar of Z1 bar, W3 of 0 has a 1 over Z1 bar. But because of the Z1 bar, that pole is killed. So you don't pick up any residue from here. Similarly, this one also doesn't pick up any residue from here. Okay, because B with C has a 1 over Z1, but this Z1 kills. So the only residue that will pick up is from here. Okay, because B bar with C bar gives you 1 over Z1 bar minus Q inverse, 1 over Z1 bar minus Q. Okay, and you have to multiply it by Z1 bar, that gives you factor of Q bar. And similarly, this gives a factor of Q. And then there's an extra minus sign because this B bar is of course anti-commuting. Okay. So to go next to C bar to pick up the pole, it has to pass through C, okay, which is also anti-commuting, and that picks up a minus sign. Okay. So the final result that you get is that this is minus 2 pi I inverse GS integral dq h dq bar. Okay. This Q inverse and Q bar inverse gets cancelled. Okay, maybe let me write it in here once. Q bar inverse. Okay. And then we have these contour integrals are now gone. CC bar W1 of Y1, CC bar W2 of Y2, CC bar W3 of 0. And then here you have W4 of Q. Well, Q and Q bar, of course, because W4 is not holomorphic. And in that process, I have picked up a minus sign, okay, and a factor of Q and Q bar. So this Q and Q bar cancels these factors. Okay. And ultimately, then you are left with 2 pi I inverse, this minus sign, cancel this minus sign, GS times integral dq h dq bar CC bar W1 of Y1, CC bar W2 of Y2, CC bar W3 of 0, and W4 of QQ bar. So this basically tells us that you fix 3 of the vertex operators at some arbitrary position, Y1, Y2, and 0. Okay. And then for the 4th one, you first strip off the CC bar factor, okay, and then you integrate it over its position. Okay. And in this case, you integrate it over the whole complex plane, with which is the integration over Q and Q bar. So this is then the expression for a general 4-point function, on-shell 4-point function. Okay. And if we have done any string amplitude computation before, okay, you might have seen this. Okay. But what we have done here is that we have derived this formula, okay, which in fact is one of the first things one encounters in studying string amplitudes. But we have derived it as a special case of the most general formula that I wrote down. Okay, so that's the most general formula for the bosonic string theory that I had written down. And this comes out as a special case of that formula. Are there questions?
Yes. Can you explain once again how the CC bar factor is taken away?
Because when you take this B bar, right, you are deforming this contour and picking up the residue, right? So remember the B bar, C bar OP, B bar of Z1 bar, C bar of Q bar is 1 over Z1 bar minus Q bar. Okay, there is no C bar multiplying it anymore. So since we are deforming this contour and we are trying to shrink it on Q and Q on this point, okay, the only part that contributes is the residue. Okay, so you pick up the residue at Z1 bar equal to Q. Okay, so but that, in that process, you have removed the C bar. Okay, and you said Z1 bar equal to Q. Right? That's the origin of this Q bar. And similarly, the C is stripped off because you need the pole in the operator product of B with C. Is that clear?
Yes, thank you.
Okay, so now we are going to study some divergences.
Can I also ask a related question?
Yes.
Why we only construct with the last pair of C and C bar? I think we can, yeah, there's some sort of construction as I understand, and we can in principle contract with any pair of C and C bar, or no?
Yes, we can. Okay, we can, but what we are doing here is that we have this contour integral, right? Okay.
Yeah, right.
You can define the contour. It's analytic function, right? This is analytic, this is anti-analytic. So you can, and these are separate contours. So let's take the this one. Okay. So you can define this contour and write it as a sum of two contours, one around here and one around here. Okay. So if there is no pole at this stage, at this point, so you can just shrink the contour and the result will catch. Okay. Because you can make the contour as small as you like. Okay. So the only reason that it's not zero is because of the pole. Okay. These don't matter because we are not deforming the contour on that side, right? We could have also manipulated it that way, that we deformed it the contour and pick up the residues from 1 and 2. It will eventually give the same result. But here we are deforming it in this way and we are just picking up the residues from 3 and 4. That's why you are not worried about the operator product with 1 and 2.
Yeah, okay, yeah, thanks.
So you are only interested in the singularities at 3 and 4. Okay, so now let's just look at the general structure of W. So W typically has the structure of e to the I k dot x times some polynomial in del m x and del n bar of x. Okay, so which means you can multiply by various factors of derivatives of x, various factors of derivatives of the del bars of x. Okay. And then of course you have to take appropriate linear combination to make sure that it's a primary. Now the operator product expansion of these, so these are integer conformal dimensions. So the operator product of these pick up integers. Okay, so the OP is, so let's take say W of z, Wi of z with Wj of z prime. Okay. So these factors give z minus z prime to the power minus some integer and z minus z prime, z bar minus z prime bar to the power minus some integer. These give you z minus z prime. Okay, this I can write, I'll write down explicitly. Okay, so if you remember the formula for the 3-point function, okay, it's the conformal dimension of the final object that you want, the final object. So if you take e to the I ki dot x, e to the I kj dot x, so this is at z, this is at z prime. Okay. And if you are trying to do the operator product expansion, the final object will necessarily have by momentum conservation I k plus k prime to x of z prime. Okay. So the power of z minus z prime that you will get is k plus k prime square by 4. Okay, because that was the conformal dimension of e to the I k plus k prime dot x minus the conformal dimension of this and the conformal dimension of this. So ki square by 4 minus kj square by 4. Okay. And similarly, z bar minus z prime bar to the power same, k plus k prime square by 4 minus, sorry, this should be ki plus kj. Sorry, this is ki kj. So this roughly is mod z minus z prime to the power ki dot kj. Okay. And these give you some integer powers. Okay, so z minus z prime to the power minus integer z bar minus z prime bar to the power minus some integer. But what this is showing is that as z goes to z prime, if we take ki dot kj to be sufficiently negative, so this blows up for ki dot kj large and negative. Okay. So which means that this integral that you see here, for example, okay, this one will blow up, okay, as q goes to 0. If k3 dot k4 is sufficiently negative. Okay. Similarly, there will be divergences here and here, but let's just focus on the q goes to 0 region now. Okay. So as these two points approach each other, 3 and 4, okay, there is a divergence. Okay. So this integral will become divergent. So this integral d to q of whatever is there, it will diverge for large negative ki dot kj, okay, which means that it actually diverges. This implies that it diverges for q goes to 0. Because as q goes to 0, y4 goes to y3. Okay, y4, let me remind you, is just q, and y3 was 0. So the usual approach to dealing with these divergences is to define the integral in the range of ki, where it is well defined, and then analytically continue to the rest of the region. And this, in fact, works quite well, works well in many cases. And to give you an example, I'll write down the result for the 4 tachyon amplitude. 4 tachyon amplitude. Okay, so for tachyons, let me remind you that Wi is just e to the I ki dot x. Okay, no parts of derivatives of x, just e to the I ki dot x. So you can easily calculate this 4-point correlation function using the formula that I wrote down earlier. And then the integral, you can show, can be admits an analytic form. Okay? And the amplitude becomes a constant times a nice product of gamma functions, gamma minus 1 minus s by 4, gamma minus 1 minus t by 4, so S here is K1 plus K2 square, that's a Mendelssohn variable, minus, in the mostly plus signature metric, it's minus K1 plus K2 square, T is minus K1 plus K3 square, and U is minus K1 plus K4 square. And you notice that if we try to use the integral representation for gamma, right? That's what you get from string amplitude calculation. These actually are often divergent. Whenever the argument of gamma is negative, this is divergent. But by analytic continuation, you can define it almost everywhere except at some integer values of s, t and u. So analytic continuation works quite well in this case. However, it doesn't always work. However, analytic continuation does not always work. And to understand when this happens, we need to understand the origin of the divergences better. Okay, and this is what I'll try to do now. So let me begin by stating some general results, okay, which I'll not try to prove, but this is true. So general result. First is that divergences in string theory, at least in bosonic string theory, in the fermionic string theory, you will see that there are some additional subtleties. But in bosonic string theory, divergences come from what are called degenerate Riemann surfaces. Okay, now you may ask, what are degenerate Riemann surfaces? So that is answered in the second part of this statement. Okay, and that is that all degenerate Riemann surfaces may be expressed as q goes to 0 limit of some plumbing fixture variable. And vice versa, that if you take a plumbing fixture and take the q goes to 0 limit, okay, then in that limit, whatever happens to the Riemann surface is what we call degenerate Riemann surfaces. Okay. So from this perspective, okay, this 4-punctured sphere that you saw, let me go back here. Yeah, one more step. Yeah, so this 4-punctured sphere, okay, in the q goes to 0 limit becomes a degenerate Riemann surface. And that's where the divergences are coming from. 3 and 4 are approaching close to each other. Now, as I said, there are also divergences when 3 and 1 approach each other. Okay. It doesn't look like the q goes to 0 limit of, that is not the q goes to 0 limit of this way of parameterizing. Okay. But if 3 and 1 comes close to each other, okay, if you want to see this as q goes to 0 limit of something, we have to just parameterize by picking this circle to be the one that divides 1 and 3 and 2 and 4. And then again, the associated q, when it approaches 0, you see that 3 and 1 come close to each other. Okay. So once you have chosen a plumbing fixture, Okay, and if you take the plumbing fixture variable to 0, it gives a degenerate Riemann surface. Okay. And the statement is that all degenerate Riemann surfaces can be viewed this way. Okay. That when 3 and 1 are coming close to each other, we have to just pick appropriate plumbing fixture variable, and then the Q goes to 0 limit will describe the 3 and 1 coming close to each other. Are there questions? So now what we are going to do is to use this. We'll use this to classify degenerate Riemann surfaces in terms of Feynman diagrams. Then we will see how it works. Okay. So first, we take a pair of Riemann surfaces. Okay, so here I have put this in bracket because we can either take a pair of Riemann surfaces and then show the punctures one from each, okay, or we can take a single Riemann surface and show 2 punctures on the same Riemann surface to each other. Okay, either way, you are not, what I'm going to describe is valid for both. So we now show 2 punctures via W prime equal to minus Q to generate a new Riemann surface. So when you do that, okay, this new Riemann surface is parameterized by an extra complex parameter. Notice the word extra. Okay, why extra? Because the original Riemann surfaces themselves may have parameters, right? Because they typically Riemann surfaces have moduli spaces. Okay, so those moduli spaces will come with their own parameters. Okay. But when you show them together, you get an extra parameter, which is this Q. Okay, extra complex parameter. So what we are going to do now, our goal, will be to express the integration measure over the moduli space of this new Riemann surface in terms of those on the original surfaces. In other words, the new Riemann surface, okay, has its own omega, okay, or because the genus has changed, the number of punctures have changed, so it has its own omega. The original Riemann surfaces had their own moduli spaces, so they were accompanied by their own omega, right? Those P forms that we had introduced. And what we want to know is how is the new omega related to the old omegas? Okay. This question may not be making very much sense, but I'm going to write down the formula where it might make more sense. Okay. So the point is that the extra factor that we get, extra factor will be dq, which dq bar, bq bar, and then there is a factor of minus 2 pi I inverse. And this, of course, is all inside a correlation function. Okay, I have written bq bar, but I have eventually to get a number, you have to put all this inside a correlation function. Okay. So these will be defined in the same way that we had introduced. And the point is that because you have these two extra parameters, we have the two integrals, dq is dq bar, and this is the extra factor that comes accompanying this. Now this minus 2 pi I inverse, right? Let me explain where that comes from. So recall that omega GNP has minus 2 pi I to the power minus 3g minus 3 plus n. Okay, it had this factor. And then you can check. So, okay. So then the swaying, what does swaying do? There are two possibilities. One is that it takes two Riemann surfaces, one with genus G1 and N1 punctured. It combines this with another with genus G2 and N2 punctured and gives you a genus G1 plus G2, okay, when you sew them together. And the number of punctures reduced by 2 because two of the punctures are sewed to each other. So it's this. Or it can take a single Riemann surface, okay, of genus G and N punctures. When you sew two of the punctures on the single Riemann surface, you add a handle, so G becomes G plus 1. Okay. And N goes to N minus 2 because two of the punctures are gone. So I leave it as an exercise to check that in either case, the integration measure, the new integration measure, new omega, you can say, so the new omega has an extra factor of minus 2 pi I inverse. Okay. So let's work out what BQ and BQ bar are. So since we have solved by W prime equal to minus Q, okay, we can write as a W equal to minus Q over W prime. Okay, let's call this F, some Fs. Fs of W prime and Q. Okay. So then BQ will be integral over, this is about, say, mod W equal to mod Q to the half. That's where the sewing is taking place, of del Fs del Q B W dW. The Fs bar doesn't contribute because that depends on Q bar. So this is del Fs del Q is minus, so del Fs del Q is minus 1 over W prime, which is W by Q. So this is 1 over Q integral mod W equal to mod Q to the half W BW BW. Okay. And similarly, BQ bar is integral W bar W bar W bar BW bar. Okay, so this gives the explicit expression for BQ and BQ bar. Okay. So what we are going to do now is to combine this with the plumbing fixture relation that we had derived earlier. Combine this with the plumbing fixture relation. Okay, this we did some time ago, so I have to remind you what it was. So let me write down the net formula, and then I think it will become a little clearer. Okay. So we have this dq, which dq bar over minus 2 pi I. Okay, this we have. Then the plumbing fixture relation, let me remind you, we had a phi r of 0, phi s of 0. Okay. And then we had phi rc, phi sc, q to the hs, q bar to the hs bar. Okay, so the plumbing fixture relation was this much. Okay. The only extra ingredient here is that we have a factor of bq bar. Okay. So here we insert bq bar. Okay. Because plumbing fixture just told you how to write down the correlation function in the new Riemann surface in terms of the correlation function of the old Riemann surface. The operator content doesn't change. But here, what has happened is that the operator content, we have inserted two extra operators, bq bar, right? And though that's lying right on the mod w equal to q to the half, mod q to the half. Okay. So that can be inserted in between phi rc and phi sc. Okay. And bq bar inserted here, okay, you can see is the bq is integral w bw dw. Okay. This is nothing but b0, okay, because if you remember the expansion of bw was sum over n bn w to the minus n minus 2. Okay, if you substitute this here, okay, you will see that you pick up basically the b0 pole, right? When you integrate around mod w equal to mod q to the half. Okay. And similarly, bq bar is integral w bar b bar w bar dw bar, which is b0 bar. Okay. So now we are going to change variables and write it in a simpler form. So we write now, we introduce r theta variable. So q we write as r e to the I theta. Okay. So this can be written as minus 1 over 2 pi I. Okay. Once you have this dq, which dq bar becomes minus 2i r dr d theta. I forgot one important thing. Okay. That we had a 1 over q here, 1 over q bar here. So this is b0 over q. Let me write it as q inverse b0. And here I have q bar inverse b0 bar. Okay. So r dr d theta, okay, this q inverse q bar inverse gives you r to the minus 2. Then we have phi r of 0, phi s of 0. Then, okay, here b0, let me write this here. Phi rc b0 bar phi sc. Okay. And here you see q to the hs, q bar to the hs bar becomes r to the power hs plus hs bar e to the I theta hs minus hs bar. Okay, so this is the extra integral that you get. Are there questions? So this is multiplied by the integration measure everywhere else, the rest of the integration measure that comes from the original two Riemann surfaces. Okay. But those don't know about r of theta, or that means those don't know about q and q bar. Okay, so the r theta dependent part is purely in this formula over here.
Sorry, Ashok. I missed how you get the R minus 2 in.
Oh, that's from 1 over q bar. The 1 over q and 1 over q bar here.
Okay. Thanks.
That gives you the 1 over r square.
Perfect. Thanks.
Okay, so now, so what is our goal? So our goal is to understand the divergence from the q goes to 0 region. Understand the divergence from the q goes to 0 region. Okay, so q goes to 0 means r goes to 0. Because q, let me remind you, is r e to the I theta. Okay. So if our goal is to understand this divergence, then we can restrict r to run over a small region around the origin. Okay. So you can take, for example, 0 less than r less than a, right? Which will correspond to, so a is a small number. And this will correspond to mod q less than a. Okay. For other regions, okay, there will be other divergences where you use a different plumbing fixture variable. Okay. So for this plumbing fixture, if you want to see what the singularity is doing, you can restrict to this region. Okay. But normally, this is not what we do. Okay, and I'll explain why we don't do this way. Okay. So you recall that q was introduced through this plumbing fixture relation, w prime equal to minus q. Okay. So if you want to restrict to this region, what we can do is the following. We write this as w over root a. W over square root of a, w prime over square root of a equal to minus q over a. Okay. And now we call this our new w, new coordinate system, new w. This is new w prime. And this is our new q. Okay. And with this feature, we can just restrict to q less than or equal to 1. Okay, so that's standardized. Okay. So in other words, if you want to restrict to close to the plumbing fixture variable, close to the singularity, okay, one way to do this will be to restrict q to be a small number. Okay. But the other way to do this is to scale up the local coordinates appropriately, so that when q is less than 1, that actually corresponds to close to the singularity. Okay. And this is the procedure that we'll be adapting. Okay, we'll assume that the local coordinates have been scaled in such a way that when q ranges from 0 to 1, we are actually very close to the singularity. Okay. This sometimes is described in the language of in the string field theory literature. Okay, this is called adding stubs. Okay, I'll not try to explain why it's like adding stubs, but roughly it's when you scale w, right? It's like adding something to log w. Okay, so and that's something that you are adding, the log of a, that's what is called stub. Okay. In any case, but what you are doing is this. Okay, we are basically scaling up the local coordinates so that when you restrict q to be smaller than or equal to 1, you are close to the singularity. Okay. So now we are ready to do the q integral, okay, in this range. Because the q dependent part or the r dependent part, you can easily see where it's coming from, r theta dependent part. So we'll just isolate the r theta dependent part from here and carry out the integral. And then we'll put together with the rest. So the q integral now gives 1 over 2 pi integral 0 to 1 dr, integral 0 to 2 pi d theta. If you collect all the, maybe I should put a 2 also outside. Okay, so these 2 basically came from this minus 2i over here, right? This minus sign cancelled, I cancelled, and that 1 over 2 pi and then 2. Okay, and then I'll just collect the powers of r and powers of theta. So you basically get r to the power hs plus hs bar minus 2 plus 1 minus 2. Okay. Where is the plus 1 coming from? Because there's an r dr, that's the plus 1, and minus 2 because there is a 1 over r square. Okay. And then e to the power I theta times hs minus hs bar. So when you do this integral, you get this as delta hs bar, that's the theta integral. Okay. And then the r integral, okay, you can easily convince yourself, this gives you, this factor of 2 is there, 2 over hs plus hs bar. Okay. This is for hs plus hs bar positive. Okay. So with this, now I can write down the full effect of plumbing fixture. Is to insert the following quantity: phi r of 0, phi s of 0, phi r c, b0 bar. Okay. This 2 over hs plus hs bar, I'm going to write in the following way. Okay. So hs and hs bar we introduced as control weights of phi s. Okay. But that also means that this is the L0 eigenvalue. Okay. So hs bar basically are L0 and L0 bar eigenvalue of the state phi s. Okay. This I didn't say earlier, but you can easily convince yourself from the various lessons that I have written down. That if hs and hs bar are control weight of phi s, then you can also think of this as L0 and L0 bar eigenvalue of phi s. Okay. And it's also of phi sc, because from the definition of phi sc, the fact that they are conjugate states, it follows that the L0 bar eigenvalue of phi s and phi sc must be the same. Okay. So this delta hs bar, 2 over hs plus hs bar, okay, I can write as 2 over L0 plus L0 bar, delta L0 bar, and then phi sc. Is this clear? Okay. All I have done is that I have put together this expression over here, okay, together with the r integral that we did, r theta integral that we did, okay, to write it as in a one neat compact form. Okay. And this one I'll call propagator, for a reason that will become clear in a minute. Okay. This, of course, is accompanied by the rest of the rest of the contribution from the original Riemann surfaces. Okay. But now we see that this effect, the fact that the effect of plumbing fixture inserts this into the amplitude, okay, can be regarded as a Feynman diagram as follows. Okay. So we can think of this as the Feynman diagram of the following form. So we have a blob over here. We have some external states. Okay. And then we had some propagator coming out and another blob with some other external states. Okay. So here, okay, these lines, this is the state phi r, this is the state phi s. Okay. And the propagator by definition is this whole object. So this is the interpretation if you do plumbing fixture on punctures on two different Riemann surfaces. Okay. So this blob represents the amplitude on one of the Riemann surfaces. This blob represents the amplitude on the second Riemann surface, and this is the effect of sewing. Okay, so the effect of sewing is like connecting the two by a propagator. The other case where you sew two punctures on the same Riemann surface can also be expressed in a similar way. So here we have external states coming out, okay, and then we have two lines coming out which are joined by this propagator. Okay. So here this is our phi r, this is our phi s, okay, and this is the propagator. Okay, so the same propagator. Is this analogy clear?
Is a question.
Yes.
Sorry, I just wanted to ask if the new Q you evoked when you wanted to understand the origin of the divergence is connected to the regularization of the Schwinger parametrization you do in string field theory when
Indeed, it is.
Yeah. Okay.
Exactly. So this is the Schwinger parameter of string field theory. Indeed.
Okay. Thank you.
Okay, I think it will become a little clearer maybe when I discuss this in a little more detail. Okay, but I should just say at this stage that you see that the fact that we are calling this propagator is more than just an analogy. Okay, because if you look at this L0 plus L0 bar, okay, this 2 over L0 plus L0 bar has a structure of 2 okay, over. There is always a contribution from the momentum piece, okay, which is k square by 4. Okay. And then L0 bar has a k square by 4. Okay. And then there is some integer, okay, which is coming from the partial x and partial x bar, partial bar x. Okay. So you see, this has exactly the structure of a 1 over k square plus m square, right? So this I can think of as 4. This is k square by 2 plus n, right? So 4 over k square plus 2n. Okay. And then this 2n effectively is behaving as mass square. So this is like the 1 over k square plus m square, okay, except that of course m is not fixed. Okay. There is a whole tower of m because n can take different integer values. Okay. Which means that this diagram that we have drawn here, you should think of this internal line as not just a single line, as a single particle, but a whole list of particles. Okay. And that's also apparent from the fact that here we have to sum over RNS, right? These are repeated indices. We are supposed to sum over RNS, and that corresponds to summing over all intermediate particles over here. So this is really the propagator, and when you go to the full-fledged string field theory, this becomes the propagator of string field theory. Okay, but right now we are just developing this just as an analogy. Okay, so with this, we can now also try to understand the origin of the divergence. So we have Q equal to R into the I theta. Okay. And Q goes to 0 corresponds to R equal to 0. So we have an integral of the form integral 0 to 1 dr r to the power hs plus hs bar minus 1. Okay. And this we wrote as 1 over hs plus hs bar. Okay. So this is an identity. This is identity if hs plus hs bar is positive. Okay. So here both sides are finite. So no confusion. So if HS plus HS bar is negative, then the right hand side is well defined. But the left hand side is divergent. Okay, so then using RH, so RHS in fact is the analytic continuation of the left hand side in this case. Okay, so here then using RHS is equivalent to analytic continuation of the left hand side. Okay, and using RHS means that you use the Feynman diagram interpretation. Okay, because from the Feynman diagram perspective, okay, this is more fundamental, right? 1 over L0 plus L0 bar. That's 1 over K square plus M square. Okay, that's the fundamental description of this amplitude. Okay, it just so happens that if you re-express this as an integral, okay, and that's the Swinger parametrization. Okay, if you re-express this 1 over L0 plus L0 bar as an integral, okay, then you run into apparent divergence whenever L0 plus L0 bar is negative. Okay. And since there is this question of Swinger parametrization, let me just write down the precise relation. Okay. So if we write R as e to the minus t, then this t becomes the Swinger parameter of the propagator. Representing the propagator. Okay, up to a normalization. Okay, are there questions? Let's go back to this integral again. So integral 0 to 1 dr r to the power hs plus hs bar minus 1 is 1 over hs plus hs bar. Okay. So the really problematic cases come for hs plus hs bar equal to 0. So here analytic continuation is not helpful. Okay, because it actually diverges. So here you don't know what to do from the worldsheet perspective. Okay, you will just run into a divergence and then you are stuck. Okay. But from the Feynman diagram perspective, you can see what's going on. Right? From the Feynman diagram perspective, hs plus hs bar equal to 0 okay, implies an on-shell internal propagator. Okay, because this is up to constant of proportionality is like 4 over k square plus m square. Okay, so this vanishing means some internal propagator is going on. So then, okay, so this is divergent, but in QFT, of course, we know how to deal with on-cell internal propagators. right? I mean, in fact, if you in QFT, you know that if you do things correctly, you will never encounter an on-cell internal propagator. Okay, so in QFT, you know how to deal with this. So what we need to do is that we need to invoke QFT. Inside to deal with this. Okay. So let me give an example of when we encounter this in QFT. Okay. So suppose in quantum field theory, you are doing a one loop calculation, okay, and you have a diagram like this. So here by momentum conservation, okay, the momentum here is the same as the momentum here. Okay. This propagator is 1 over k square plus m square, okay, where m is the particle mass of the particle that is flowing in this line. Okay. And if the external line is the same particle, then we know that the on-shell condition on the external line forces k square plus m square to be 0. Okay. So k square plus m square is 0 by on-shell condition. So this is 1 over 0 by on-shell condition. Okay. So this is a Feynman diagram where you will encounter divergence in quantum field theory if you naively try to sum over Feynman diagrams. Okay. So using this insight, you can also figure out where will such divergences come in string theory. Okay. All you have to do is to just fatten these into pipes. So this is in QFT. This is in QFT. Okay. Now in string theory, if you fatten, let me draw the diagram then. So this is like one particle coming in, then it goes into a loop. Okay, that's the torus. Okay. Then it goes into this kind of diagram. Maybe okay, this is the whole thing I have represented by sphere, but you can also refine it. Okay, it doesn't matter. But what we see here is that when this snake goes on shell, right? So this is Q. Suppose this plumbing fixture variable is Q. Okay. So we can be sure that for a diagram like for an amplitude like this, so this is genus 1 4-point function, right? You can see there is only one handle and 4 punctures. But in one particular degeneration, which is shown here, okay, we can be sure by comparing this with this that Q goes to 0 limit, produces a divergence. That cannot be tamed by analytic continuation. Okay. Basically, because what will happen is that you will get an integral like integral d to q over mod q squared to the power q squared to the power or mod q to the power k square plus m square, maybe with some multiplicative factor. Okay. And because k square plus m square is forced to be 0, right? This external state is on shell. Okay, this is forced to be 0 because of the external state being on shell. Okay, this just becomes 1, right? For k square plus m square equal to 0. So there is a ki dot kj kind of term. So this will produce a divergence. So this is infinite and cannot be analytically continued. Okay, other questions? So we know what the remedy is in quantum field theory. So remedy in QFT is to resum. Right? We resum if you call this sigma 1pi diagrams, this becomes 1 over k square plus m square the sigma of k over k square plus m square whole square. Okay, so roughly this is 1 over k square plus m square minus sigma of k. Okay, so you have to first resum the external propagator by keeping this off shell. Then, so this is first resum, then look for pole position. This will be a mass renormalization. Okay, because the pole position will shift. And then we finally apply LSZ to calculate S matrix. So in string theory, exactly the same procedure has to be applied. Okay. But for this, we have to learn how to systematically organize the amplitudes into sum over Feynman diagrams. Okay, so far I have just introduced one propagator. That's not enough. We have to take a string amplitude and break it up into sum over Feynman diagrams. Okay. Once you have done that, okay, and once it has exactly the correct structure of Feynman diagram of a quantum field theory, then you can carry out this procedure exactly as in quantum field theory. Other questions? The main advantage in string theory, of course, will be that this sigma of k, which in quantum field theory is ultraviolet divergent, okay, will not be ultraviolet divergent. Okay, it will be perfectly finite because it will get contribution from integration region, okay, that doesn't involve degeneration. Okay, because all degenerations will be separating out into the propagators. So let me now then outline the 2 steps that one has to follow. So the step 1 is to organize the off-shell amplitudes. I have already told you how to compute off-shell amplitudes. Into sum over Feynman diagrams. So this is a non-trivial step, will be described in detail. So once you have done that, then the step 2 is just straightforward QFT. Okay. So we follow the usual QFT techniques. To deal with on-shell internal propagators. These I am not going to discuss in detail. Since the procedure is identical as in QFT. So let me then describe is how to deal with step 1. Okay. But maybe I should just say also one more thing here. Okay. And that is to note that since all divergences in string theory come from q goes to 0 limit of some plumbing fixture variable, which will translate to on-shell propagator we see that there are no ultraviolet divergences. Because on-shell, the divergences as well as on-shell propagator are more of the infrared kind. And this will, we know how to deal with in quantum field theory. Okay? And these are independent of the ultraviolet divergences that we encountered, which are simply not present in string theory. Because it is in this sense, one says that string theory doesn't have ultraviolet divergences. Okay, so let me then begin with step 1. Okay, we'll see how far we can go today, and then may have to complete it next time. Okay. So the step 1 is that we begin with 3-point function. We begin by specifying off-shell 3-point function. Now, 3-point function is associated with the genus 0 3-punctured sphere. Okay. So M03, okay, this is 0-dimensional. Okay, it again follows from this formula 6g minus 6 plus 2n. Okay, g is 0 and n is 3, so that's 0. So to find a specify off-shell 3-point function, we need a section of P03. Okay, section in this case is 0-dimensional. This basically means that you choose some local coordinate 3 punctures. Okay, so which I'll write as a equal to fi of wi for some functions I equal to 1, 2, 3. Okay, so the choice of 3-string vortex, okay, or the section of P03 basically means that we specify a set of 3 functions fi on the fi of wi. Okay. So then the amplitude, there's no integral involved. Okay, it's simple. So it's f1 dot v1 0, f2 dot v2 0, and f3 dot v3 0. Okay, because the punctures are located at wi equal to 0 in the wi coordinates. The ith puncture is at wi equal to 0. Now the choice of fi will not be totally unconstrained. Okay, so let me just explain how we should choose what condition we impose on the fi's. Okay, and that again comes from the usual idea from Feynman diagrams from quantum field theory. Okay. So we'll put a constraint that will choose the fi's such that A, V1, V2, V3 is invariant under permutations of V1, V2, V3. Okay. Whereas invariant, it's invariant up to sign. Because if, for example, V1 and V2 are Grassmann odd, which can happen if they carry the appropriate Gauss number, then it should be antisymmetric under the exchange of V1, right? So invariant is up to that sense. Now there are two ways to implement this, okay, or two extreme ways, which I'll discuss. So there are two ways to implement this. So the first way is that given any permutation, of 1, 2, 3, let's say any permutation P of 1, 2, 3, there should be an SL2C transformation such that this SL2C transformation, let me denote by H, such that H of Fi of Z is F of Pi of Z. Okay, so Pi means whatever I becomes under the permutation. Okay. So if this is the case, then because the correlation functions are SL2C invariant, okay, you will be guaranteed that the amplitude is symmetric under the exchange of the VIs. Okay. So this I'll leave as an exercise for you to check that if this condition holds, then the amplitude does satisfy the required permutation symmetry. This may not always be possible. Maybe too restrictive. Maybe let me put it this way. Maybe too restrictive. Maybe possible, but only a very few spatial choices of F will do it. So there's an easy way to implement this symmetry. Is to just symmetrize. Plus other permutations of F1, F2, F3. Okay, so you place F1 by F2, F2 by F1, and so on. So this will be manifestly symmetric, right? So you can also define the off-cell amplitude this way. Okay. Now this one has an interpretation in terms of PGN. Okay, let me write. So M in this case is 0-dimensional, right? So P is just a line, right? So let me write P is 0, 3 here. Okay. So normally, okay, choice of a section means in this case that you have to pick a point, right? This is a choice of a section. If you decide to do it this way, okay, then this is like you are taking the section, okay, as the average of 3 points, 6 points, okay, 1 over 6 times, if you call these points S1, S2 up to S6, this is a formal average. Okay, but the meaning should be clear of this formal average. Okay, so this we can call a generalized section. Okay, and for many purposes, generalized sections are useful because a single section may not be the right thing to use, may not be a very convenient thing to use. Okay, so this is something we should keep in mind, that when you're talking about that we choose a section to specify the off-cell amplitude, we have a choice of taking averages of sections. Other questions? Okay, so now we go to the first non-trivial step. That's a 4-point function. So once you have chosen F1, F2, F3, we construct a 4-point function. A sphere with 4 punctures, or a family of family. Oops. Four-punctured sphere. By plumbing fixture. Which means that you take 2 of these 3 punctured spheres. Okay, the local coordinates are fixed already. Y is F1, F2, F3. And because you have symmetrized, it doesn't matter which one you use. Okay, so this, let's call it 1, 2, 3, 4. Okay, here whether we are which one you are showing, it doesn't matter. So let me. So you take here mod W equal to Q to the half, mod Q to the half. Okay, this is mod W prime equal to mod Q to the half, and then show them. So this provides a family of 4 punctured spheres. Okay. Together with local coordinates at the punctures. Because already for the 3 punctured sphere, you have chosen local coordinates, right? So the same local coordinates you'll be using on the 4 punctured sphere. So this provides a family of 4 punctured sphere. Okay. So this you can think of as a segment of a section in P04. Segment of a section in P04. Okay, because all the local coordinates are specified and you have a family of 4 punctured spheres, a 2-parameter family. That's exactly the dimension of M04. So in terms of Feynman diagrams, so what you can think of as what you are doing here is that once you have defined this official 3-point function, okay, you are basically showing and constructing a 4-point function. Okay. And here I restrict Q to mod Q less than or equal to 1, as you have been doing earlier. Right? So that you exactly get the propagator that we introduced earlier. Okay. So here is 1, 2 on one side and 3, 4 on the other side. Okay. So this we can call the S-channel diagram. Similarly, we can construct the T-channel diagram where you have 1 and 3 on this side and 2 and 4 on this side. Right? That will give a different section segment. Because it will still give a family of 4 punctured spheres together with local coordinates of the punctures, but it will be a different segment of the section. Yeah? Because you are considering this is a region near the degeneration where 1 and 2 come together. Right? This is the one that I have shown here. Okay. If we replace by 1 and 3, then that will cover the region where 1 and 3 come together. So the general picture then is what we have is in P. If we draw P04, here is M04. Okay. The S channel gives you this, let's call it S. Then you have a T channel and U channel. Okay, each of them gives a section segment. Okay, and the idea is that we now fill the rest in some way. Okay, there is a lot of freedom. Okay, except that the boundaries have to match up. Okay, and this thing that we fill with, we call S prime 04. Now, because I have drawn it in one dimension, it looks disconnected segments, but actually this you can show is connected. S prime 04 is actually connected in 2 dimensions. So what's the interpretation of this? So the interpretation of this S prime is that this is representing a contact diagram. With V1, V2, V3, V4. And the expression for this is we have a GS factor. Okay, all these I'm reading out from the general amplitude formula that I wrote down. Integral of S prime 04. Okay, omega 04. Okay. This is a 2-dimensional section. So this is 2 form. We pick the 2 form. V1, V2, V3, V4. Okay, and again we want to choose S prime 04 in such a way that this is symmetric under the exchange of V's. Okay, so this we choose in such a way, choose such that it is symmetric. Under exchanges of V1, V2, V3. S, T, and U channel diagram by definition are symmetric. They permute into each other. Okay, because that's the way you have to construct a 3-point function. But for the 4-point function, you have to make an effort to make sure that this contact diagram is symmetric. Is this clear? Are there questions? So I think, see that my time is getting up. So let me just say what I'll do next time. Okay. So next time we'll take the same 3-point function. Okay. And now construct this one. Okay. Joining the 2 lines from the 3-point function. So this will be the Feynman diagram, right? The interpretation in terms of the Riemann surface will be that you just show them. Okay. So this will again cover part of the integration region of 1 puncture torus, right? So this is 1 puncture torus. Okay. And then you cover the rest, you cover by a contact diagram. Okay. So this will give the rest. Okay. And the interpretation of this contact diagrams will be that this is like a 1-loop counter term. Counter term in quotes. Okay, but it's like a counter term that we add in quantum field theory, except that this is needed for gauge invariance. And not UV finiteness. Because the counter term by itself will be finite, because this involves integration over regions which do not have any degeneration by definition. Okay, counter terms are always integration over regions which do not have any degeneration. Okay. So it's a finite counter term. Okay, but it's needed for gauge invariance. And then we'll see how to do this systematically for all amplitudes. Okay, but you can already guess at this stage how we'll organize the string amplitudes into sum over finite diagrams. Okay, so I think I'll stop here and then we'll continue next time.